Very good. Yeah, so project initiation, specification development, conceptual design, detailed design, delivery, redesign, maintenance. Some of those things come at the end. Who is here for user need lecture? You guys are here. Yeah? Okay, who's here for the user need lecture? Anybody? Can somebody give me a definition for a user need? So what do you think that might mean? Okay, nobody. All right, user needs are the primary features of the product. So if you're talking about a car, it should be able to drive forward and backward, and should be able to be, you should be able to steer. You should be able to put people inside of it. Those are the basic features. So those are user needs. What about a specification? You said you were in the specification lecture. What is a specification? Right. So that's a user need. The specification takes that and makes it quantitative, right? So some of the things we talked about in a specification, they should be exhaustive or complete. So it should completely specify your entire project or product. Some of the other things about specifications, they're not self-conflicting. So we said user needs can be conflicting, right? So I could say I want this part to be durable and cheap, and those are often in opposite directions. But in specifications, we say a number. So we say it should be under $100, and it should last for 1 million cycles of wear. And maybe there's a design that can meet both of those at once. Okay, so it has to be self-consistent, and it has to be quantitative. So it has to be verifiable. So we talked about verification and validation. A specification needs to be verifiable. You should be able to run a test and get a yes or no answer as to whether you satisfied it. So that's specifications. Are the needs of them. So that's generally gets you through the process of design up into the actual design. And it's kind of funny, design is a purely mental exercise. So there's really nothing in the design phase that you have to show for until you create the design outputs. Okay. So the design happened in your brain, and then what you wrote down to communicate that to someone, that's the design outputs. So I'm going to walk you through, get a little light up here, this engineering design process in kind of a cartoon form, just to give you some idea where do the design outputs come into it. So let's start with the user. That's where we always start. He's a stick man. He's unhappy because he has a need. His need is he has no foot. Right? So we'll bring one of you clever engineers in here. Make a curly-haired engineer, friendly. And the engineer is going to notice this user need. So this is the project initiation phase. Right? So engineer has a customer, user here, say he needs a foot. So at that point, she's going to say, I've got a project, I know what it is, I've defined it, I'm ready to go into specification development. So she's going to write some user needs. Right, so this is spec development phase. So first she'll write some specs. So a specification for this foot that she's going to design, stickman, maybe specification 1, maybe it needs to be load bearing. Right? And specification 2 might be it needs to fit in a shoe. Seems like some basic user needs for a foot, right? Give this nice fella something he can walk around on. So, sorry, I called these specs. These are user needs. Nobody even caught that. Are load bearing or fits in a shoe quantifiable, quantitative? Not really, right? But they are the basic features of the product. So these are the user needs. So you come up with user needs, and then once those are done, then you're going to come up with specs. So let's come up with a couple of specs for load bearing. We have spec 1.1, right? So user need 1, spec 1.1. It's load bearing, let's say, should withstand 2 times body weight. Okay. 2 times body weight, static. maybe 1.2 is a fatigue. Maybe we have one-time body weight for 1 million cycles at 10 hertz. Okay, so I can run a test for that spec. So I'm going to load it up with body weight, run 1 million cycles at 10 cycles a second. Okay. So there's a couple of specs. Fit and shoe, we could do the same thing. We can have 2.1B length less than equal to 7 inches. Right? So there's a specification you could write to this user need fits and shoe. Right? Does everybody see how this is progressing? So this is the specification development phase. So she's got that done. Our engineer has some specifications to design to. So now she's ready to come up with her big idea. So she's in conceptual design phase. So in conceptual design phase, she's over here. She's a good engineer, right? So she's got a big idea. What if I make this guy a little kind of hook with a spring on it, takes some of that load, and then a big pad at the bottom for a foot? And that's her conceptual design, okay? So at that point, she's going to give that back to the user, or check with him, and get feedback, and she's going to iterate. So she's going to prototype and iterate. So this is where you'll spend a lot of the time in design. And this is really the fun part. This is what we all like to do, right? So we're going to sit around, we're going to come up with cool ideas for this foot until we get something that'll work. And once that is done, once you have prototyped and iterated until you have something that meets your specifications, makes your user happy, then you go on to detailed design. And that is what today is about. So detailed design doesn't look like this idea anymore, where she came up with the concept. Detailed design looks like a print. So now she's got her part, the base view, and she's got some kind of a spring built in. There'll be a couple of views of this part. And she'll state what the material is, have some information in this print. And so now she has a document that can be manufactured to. That's detailed design. I don't know why it's buzzing. So this is where we are in the project. So in EPICS, what we tend to do is we go through all the first steps of this really well. We write our specs. We do conceptual design. We prototype. We run through this prototype loop. And when we get done with the last one of those prototypes that we like, we deliver it back to the user. So we kind of stop right here. Very few of you go through and create a print, right? Probably most of you haven't done that. So this is something to learn as you get into your career as an engineer. How do you go from a concept to something that can be manufactured to? So that's kind of the basic flow. So where that takes you to is the end of detailed design. So now what we miss in our thing is production, right? So a lot of today is going to be how do you go from detailed design into production in order to deliver. Does that make sense to everybody? Does that build a little example as to what this is all about? I still get a lot of blank faces on the engineering design process after a number of weeks. It's buzzing. All right. So design outputs define the design. So when you get through and you build that last prototype in your conceptual design, most of you will call that your design. Here's our design. Here's what we came up with. But that's not actually your design. That's an instance of your design. So those of you who have done any programming, you'll have a class and an instance of a class. So here's a prototype of a circle. That's your design. An actual circle is just an instance of that. So that's really where design is all about, and that's what engineering is about, is coming up with that prototype of the circle, right? So this is what a circle should be. It's not about the individual circle. So if you think about Lego, what does Lego value more? The design of the Lego or an individual Lego brick? No, the design, of course, right? So they produce billions of Legos. So one Lego isn't of any real value. That's not the design. That's not where their intellectual property is. It's in that piece of paper that's the print at the end, okay? So there are a number of documents that create design outputs. Print being the most obvious one, but there's actually a lot of things. So there are manufacturing routings. So routings are like in a recipe. Routings are the steps. You have a bill of materials, which is like the list of ingredients in your recipe. So your list of ingredients, your bill of materials, will tell you what materials you need, raw materials, what stock parts you're going to put into it. And then your routing will tell you what machine you're going to cut parts on, how you're going to assemble it, fabrication, things like that. Okay? Some things you wouldn't think about. Labels, your manual, any kind of trademarks that you would have. These are parts of your design that define what the product is. And then your inspection criteria, so that's how you're going to check the part when you're done, and your testing results. So all these things define the product that you're making or the project that you're making. So those are really the core of your design. So I'm going to go into some detail on how to do a print. How many of you are in an engineering field that produces physical things? Just two? Two of you produce physical things? The rest of you are software engineers? Okay, one hand at a time. So those of you who are electrical engineers, you produce physical things. Mechanical engineers, you produce physical things. Civil engineers, prints are your whole life. It's all you'll ever do. So software people, you have a little wiggle room here, but a lot of the same principles will apply. Just in how to document properly what you're doing and communicate it so someone else can produce it. Because if you're an engineer and you produce a product that only you make, you're probably going to be unsatisfied with your engineering career, right? So the guy who designed this little button clicker, he doesn't make these, but he designed it, right? So that's your job, not to make it. So first thing that most of you would think of in creating a print is making a CAD model. So a lot of you will get this far so that you can 3D print something, because that's the easy way to make part. So this basic model I created here, you've got this teal handle, okay? And there's the orange shaft that goes through the handle, and it's caught in the handle with this green cross pin, so that the handle can lift up until this hits the green cross pin, or you could push it down until this face contacts down here, okay? So it's not meant to do anything, it's just a simple assembly to demonstrate how you do an assembly print, okay? So this is your CAD model. This does not define your part. So I could make this part a lot of different ways that would function or not function the way you intended if I just know your geometry. So you've got to go a step further and make the print, okay? So this is a print of the handle. So this was that teal part on the outside. So a number of things that you'll notice right away. There's a border around this print. You've got numbers along the sides and letters along the top and bottom. So those are very important when you go to communicate with someone who's going to manufacture your part. So a lot of times they'll be somewhere other than you are. And if they want to ask you a question about this length dimension right here, they'll tell you it's at F4, and that'll tell you where on the part you're looking. So that doesn't seem like a big deal on a part this simple, but I promise you, you've got 200 dimensions. It's very difficult to communicate about dimensions over the phone or with someone who's not in the room with you. So it really does help a lot. So that's key. Down here in the bottom right, you have what's called a title block. So this will usually have your company's logo. It'll have the project title, the part number or drawing name, and it'll have who drew the part and who designed the part, so that when there's questions, they know who to contact. Okay. So this is in CATIA. If you're designing a part in CATIA, I can give you this template. If you're designing a part in something else, I can help you get a template. They're usually always built in, and you can just substitute your information. But this is key to making something that is an official print that can be manufactured too. My slides shifted off a bit. The next thing you'll notice is you've got a base view, which is way up here at the top, and then two projection views. So one to the side and one below it. So a base view, you'll pick one way that you're looking at the part, and then the projection, you'll rotate the part down and to the side. And if you have a more complex part, you may have more projections, okay? So that's a pretty typical layout. So here in the base view, you'll notice how to dimension. So here's the major diameter of this cylinder. You've got this is a symbol for diameter of 25.5 millimeters. And then there are two numbers beside it. Those are the tolerance for that dimension, okay? So the upper tolerance tells you how big it can get compared to this, and the lower tells you how small it can get. So this diameter has a +1, -0 tolerance. That means I would accept any diameter between 26.5 millimeters and 25.5 millimeters. Okay? And so there's a lot of reasons why you would specify things in different ways, but that's the basic format. Okay, so anytime you look at a print, you don't know what all these numbers are, that's just telling you the range that you will accept. Because as long as you have a fine enough measurement tool, you can never make a perfect part. Okay? So if it's supposed to be 25.5 millimeters, you will never get 25.0000000 forever. Right? There's no perfect manufacturing process. You have to state some tolerance band. And depending on what the part is for, you'll have a different tolerance band. So if it's something that was like the outer casing and it has no real functional value, it's just for looks, you may have very big tolerances so that fewer of your parts that are made are outside the tolerance band. Whereas if you have a fine precision part that's moving in an engine, you may have very tight tolerances so that it can't move at all outside the functional range. The other thing you'll notice here is there is a scale, so it's a 2-to-1 scale. In this particular view, usually you'll have a scale for the whole print and then scales for individual views if they're outside the regular print scale. Next thing you'll see this A arrow going to a dashed line. That's to indicate a section view. So a section view, you take that view that you see where you draw the section line and you slice it through that, and then you open it up, and that's the view that you see. So that indicates to you where the slice happens. We'll see that section view in just a second. Here's the other projection. You can see I've got a dimension for the length of the slot. I've got 2x next to the radius dimension to tell you that there's 2 radii. Now the mistake that I made here when I drafted this is that this slot right here isn't dimensioned to either end, so that slot could drift in and out, and my print wouldn't specify that that was incorrect. So you have no way to measure where the location of this to know that you did it right. Okay, so that's a mistake. So things like that you got to keep an eye out for. Your dimensions on a print should completely specify every feature so that they can't move outside of your intended place. Okay, and that's the same thing when you're actually creating CAD. You should have everything completely constrained so that it can't move on accident in space. Okay, and then here's that section view. So where you see the hash marks, that is what would be solid where you sliced the section view, and what is clear would be the solid material behind it. Okay. So that's where you're looking into the part. So this would be the walls of the handle. You can see through to the slot. Views like this are really good for things you can't see in any of the other views, like this chamfer that I've put down here in this sleeve in. So I've got a 1 millimeter by 45 degree chamfer. You couldn't see that in any of the other views, so the slice was necessary. And there's a section view tag down at the bottom to show you where that is. So that's the kind of basic views of a print. Okay. There's the title block we talked about a little bit, so you can see you indicate who made the part, what the part was, and then the part revision. So part revision is very important. So as you update or change the part, people can tell what version you're referring to. So when you put this part into an assembly, you may have built your assembly with the revision A, and the part may get revised 2 or 3 times and may simply not be updated, and then you can run into issues. So that's a way to check. Okay. This is an assembly print. So here's the handle all put together. So same kind of thing. You've got the base view and 2 projection views. Here's the section view. This time I drew it through this view up here, so you can see the crossbeam. Okay. So the things that you'll notice are different. There are a set of bubbles up here with numbers. That's indicating what the parts are. So there are 3 parts here. The notes down in the corner. So the notes on the last print told you the material, the surface treatments that you do to the material. Okay, so those are very important to specify. Because if you had, I think I indicated a Rockwell 40 minimum heat treatment and a glass bead blast. So those specify how hard the part is and what the outside surface is like. So if you didn't do that, that sliding fit between that inside and outside part could be something else, right? If you just leave it as machined or if you did some other surface treatment. So it's important to fully specify not just the geometry, but anything else, processing steps that you want done to the part. Okay? On an assembly print, you will have instructions, it's a little covered up here, on how to assemble the part. Okay? So the instructions down here will tell you insert part number 2 into part number 1, and then insert part 3 through part 1 into part 2 and press fit. So these sequence of steps that you need to assemble the part are included. Does that make sense to everybody? Everybody following along? Okay, good. So assembly print, very similar to a part print, but showing you how to assemble. The other part you'll see here is you add in a bill of materials. This is different than an overall bill of materials document. This just shows you what is involved and what's in the print. Okay, so this part would have a bill of materials that would have extended information like what labels go in with it, what packaging material, what user manual. So your product bill of materials will have more than what's just in the bill of materials of the part. But this is the ingredient list for this assembly. Okay, so you'll see there we've got part numbers. These are just 1, 2, 3. You'd usually have a more complex part number. And then you've got the name of the part and how many of them are included. Does that make sense to everybody? Okay. I know this is not the most fascinating topic, but this is what you'll spend very much of your engineering career doing. So learning how to do them well is important. And the reason why you care about this as an engineer is because when you go into a production environment, the people who make your parts will mess them up. And you'll be very serious about getting them exactly the way you want them. And this is how you control it. Because this is where you can state exactly what that part is supposed to do and how it's supposed to work and how it's supposed to be made. Okay. So then when you have someone other than you make the part and they make it wrong, you say, no, it's supposed to be like this. So that's why the print is vital. So those tolerances that you saw in the print, where do those come from? How do I know what my tolerances should be? You know what your tolerances should be through tolerance analysis. So this is a large and complex topic that could also take a lot of time. I'm going to teach you the most simple and most safest way to do it, the safest way to do it. But I do want to give you an indication that there are some other ways, maybe better ways to do it. So we're going to do a worst case stack up. So worst case stack up says I can make an infinite number of parts and they will never fail to mate properly because I'm only going to allow parts that could mate properly. Okay. Other ways of doing it, statistical tolerance analysis. So if you were making enough parts like Lego does, you will allow some parts that could potentially not mate, but you're going to say, I know that I'm making enough parts that it's unlikely that those two will come together. Okay, so you'll know what the mean and what the tolerance is on a given machine that you make parts on, and you accept that risk that they could not fit together based on the statistics that you have. So you may say, I'll allow 1 in a billion combinations to not meet. If you're making a medical device, you never ever want that to happen, so you'll use worst case. Right? So if you're making somebody's pacemaker and they're going to be in surgery and they're going to put two parts together, they better go together every time. So you'd want to use worst case. So if we look at this assembly, we've got the shaft of this part, and then we've got a handle that it's fitting into. So if we need this shaft to fit inside that handle, we're going to be interested in the diameter right here. So I think this was 10 millimeters. And the diameter right here, which I believe was 10.5. So what I need to do is specify the upper and lower tolerances. So we're going to call this dimension A. So we'll have A upper, AU, and A lower. So that's my upper and lower tolerance. Can anybody read that if I need to make it bigger? Okay. Okay. And then on this, we'll call this B. So we'll have a B upper and a B lower. And we're going to consider these at something called maximum and least material conditions. Remember to call it least material, not minimum material, because minimum and maximum both start with M, so when you make an acronym, that's kind of hard to remember. So if we call it least, we can call it LMC. So at these two conditions, they set the outer bounds of where the part will be allowed to be. So at at the nominal condition, which I show on the top here, you're stating the size of the shaft somewhere smaller than the size of the hole, so that you know it will fit in, but it won't toggle too much. So that's your ideal. This top is your ideal. That's where you want it to be. Your maximum material condition is saying I'm going to let any pad, in this case the shaft be as big as it can be and the hole be as small as it can be. So I'm taking the least material out of the hole and the most material I can have in the shaft. Right? So that's the condition in which you're interested in interference. Will that part actually fit in that case? Okay. Least material condition, you're looking at slop in the part. So how much am I going to give wiggle room in this part? So in that case, you want to take whatever your pad would be and make it as small as possible. So in this case, the shaft is as small as it could be, and the hole as large as it could be. So that gives you the loosest condition that you could have. Usually MMC is the more critical. Usually you can kind of guess your way at how sloppy you'll allow it to be. But you really have to check maximum material condition. So you'll say at maximum material condition, so MMC, we need 10 millimeters plus our upper tolerance to be less than or equal to our 10.5 millimeters minus the lower tolerance. Does that make sense to everybody? So you're just saying, here's how big that is nominal plus how big I'll let it be with my tolerance, and subtract that, and make that less than the size of the hole at its lowest size. Sorry, this is the lower. Does everybody see where I get that? It's algebra, but see where it's coming from? So if you do the algebra here, take the 10 across, and you've got 0.5 millimeters. It has to be greater than A upper plus B lower. So what that means is the sum of those two tolerances has to be less than 0.5 millimeter. So I can choose what these tolerances I want them to be, so long as I'm under 0.5 millimeter. So I could set them both to 0.1, but I'm wasting some of my available band. So what I'm going to set them to, I'm going to say it's generally easier to hold the tolerance of a hole than the tolerance of a shaft, because you're drilling a hole and you're turning a shaft on a lathe. So I'm going to give myself more room on the shaft. So I'm going to set AU equal to 0.4. And then I know for BL, for the lower tolerance on B, I can have 0.1. Does that make sense to everybody? So I'm just taking my 0.5 and I'm choosing not to make them even. I'm picking what I want so that I can manufacture easier. So I've got 0.4 for my upper, and 0.1 down here. And you make that negative because that's a lower tolerance. Okay? So at least material condition, you do a similar operation. But what you're really interested in is how loose you'll allow the shaft to be in the hole. And you could do some geometry and say I'll allow it to go to 10 degrees or some angle. What your bound is kind of arbitrary depending on your application. Okay, so it may be that you just want it in there. You don't care how loose it is. We'll say, for the sake of doing the calculation, that you'll allow a millimeter. So you're saying my total gap should be less than or equal to a millimeter. It's kind of like an M. So your gap is equal to the difference of the nominals. So it's equal to 10.5, and then you're at the maximum condition, so you're going to add BU minus the 10 millimeters for the shaft at its least condition. So that's going to be at subtracting out a lower. Does that make sense, everybody? Okay. So at this point, you say I've got this equation needs to be less than or equal to my 1 millimeter. So I know 10.5 minus 10 would be half, and I can subtract that across, and then I'm going to sum BU and AL. So I know that BU plus AL need to be less than or equal to 0.5 millimeter. And maybe in this case, I don't care which one I give more tolerance to, and I'll make them equal. So I can set BU equal to 0.25 and AL equal to 0.25. So I can set both of these equal to 1/4, and they'll be negative, and this one will be positive. So that's how you could come up with a set of tolerances for those dimensions based on not allowing interference at the top end and giving a millimeter of slop at the least material condition. Does that make sense to everybody? Math's pretty simple if you get where I'm pulling the numbers from. Does anybody need to go over that again, or good? It was interesting enough that time? Okay. Good. So with that, you could dimension those, and then for each dimension in the print, you'd go through and do a similar exercise. If you do this a couple of times, you'll start to see where the math comes from, and you can skip most of that algebra. In fact, I'm not sure I've ever done that on a real print. You just look at it and say, I can calculate that I've got 1/2 millimeter between them, so I know I can go 1/2 millimeter of tolerance overall, and then just split it out as you need to. So common sense will come to rule once you've done this a couple of times and you understand where the numbers come from. So any of you who are going into mechanical or civil, you'll definitely do this. If you're in electrical, there's a good chance of that. So those of you saying, but I'm a double E, this is a PCB. Does this kind of look similar to the print we showed just a minute ago? So you've got a picture of the part with dimensions. You've got a set of notes that tell you how to make this part and what it needs to do. You've got a title block down here that tells you what the part is, what the part number is, who made the part, what the revision is. It's the exact same thing. Okay? So just because you're in an electrical field and you think you play with Arduino and make circuits, when you go to work, you still have to do this kind of thing. Okay? Is that fair? All right. So that was all really dry and boring, so now we need some more entertaining interlude.
I wanted to have a bunch of my friends over to watch TV, not unlike this TV that just showed up magically. And not everybody can fit on my one couch. And I thought to myself, well, what if there was such a thing as a bunk bed, but as a couch? Introducing the double-decker couch. So everyone could watch TV together and be buddies.
That's literally the dumbest thing I've ever heard.
Sweet, fine. Doesn't matter. That's my idea.
So some of this subject is dull, but if you want to be master builders, you have to learn how to do it. So that's how you make a print, and that took forever to talk about a print, right? But prints are just the beginning, so you still have to actually make the part once you get that done. So a couple of things we talked about already, the router and the bill of materials, it's like the ingredient list and the recipe, right? Tells you how to make the part. So if you go to walk a part through a factory, you'll follow a router. And the router pulls off the bill of materials to know what materials to use. The other piece is CAM, so the physical model you do with computer-aided design. The tooling path that you use to make a part is computer-aided manufacturing, so that's the CAM. So if you're a manufacturing engineer someday, that'll be a big part of your life. This is a 3D printer. This is what you guys all default to all the time because you're lazy and you don't know any better. But if you look around yourself at home or here, how many items do you see that are 3D printed that you're walking around using? Probably none. If you have some, you made them, right? You didn't go to Walmart and buy a 3D printed something. It's a terrible way to produce parts on a scale, okay? So the only things that I've seen in a production environment that were 3D printed were like patient-specific medical devices, because you could scan a patient's anatomy and print them, and it's really cool. And in the future, 20 years from now, you guys will probably make everything on 3D printers because they'll be fast and cheap, but today you don't. So some real methods for making things, okay? So we've got a number of them here. I don't expect you to know how to do them, but you should know what they are. So a casting is usually associated with fabricating a metal part. So you, for instance, in a lost wax casting, you'll create a piece of wax in the shape of the part you want, and you'll dip it in a ceramic, because the ceramic can take a lot of heat. And then you melt the wax out, and you pour molten metal into the ceramic. Then you cool the metal in that shape, and then you crack the ceramic off, and now you've got a metal part in that shape that you desired. Okay? So it's lots of steps to get there, but once you do that, you can make a whole bunch of those waxes, which gives you a whole bunch of the castings, so you can make those metal parts quickly. Molding is a similar idea, but for plastic. So this is how the Legos were made. You have two metal dies that go together, you inject the plastic in, let it cool, and pop them out. You get lots of parts fast. So you can make 1 billion Legos for 1/10 of a cent each, and then you sell them for $50 for a box. This is a good business model. Machining, this is a 5-axis mill. So if you think about milling, if you think about using a lathe, things like that, these are machines. It's a subtractive way to make a part. So you start with a big block of something and you cut it out. 2 types of those, manual. Not much in production is manual, but you might use that down in the AFL. The other is CNC, which they also have down there. That's computer numeric controlled. So that's where you take your CAD model and you plan a tool path off it. Okay? So that's the CAM part we talked about. So you can do those things manually. Most people don't. Stamping is where you take sheet metal usually, and you can punch and form it in one step. It's very cost effective. Forging is deforming metal into a shape. So you think about hammer and anvil on a sword. That's forging. Modern forging usually use a tool, and you'll use a hydraulic press, something like that, and press the material in. Forging gives you really strong parts, but it's relatively expensive. And then welding and brazing are a couple of techniques for adding things together, okay, for fitting parts together. So there are a lot of different manufacturing methods. That's by no means an exhaustive list. But these are things that you'll have to use. So I'll give you a quick, I think we got time, video of a router in action, a mill actually in action. Router and mills are very similar. It does not allow playback. Maybe I won't. We'll skip that. They were cutting out a guitar body. It was neat. So once you get done, you've made the print, you've made the part. You have to check the part. So in the design phase, 2 things that we'll talk about in the next 2 lectures, risk analysis and testing. I promise next lecture is not as much me talking to you, more activity, but risk analysis and testing, these are 2 things that if you're a design engineer, you'll do. Inspection, this is something you'll do as a quality engineer. So this is in production, you make a part, how do you know that it matched that print that the design engineer came up with, okay? So a couple of things you'll do there. Criteria. Criteria are a document where you go through the print, determine which of those features are critical to quality, and you inspect those and check those parts. Gauges are a tool that you'll use for measuring parts. So a couple of dumb tools we have down here, tape measure or a set of calipers, depending on what kind of resolution you need. You can check a single dimension. A gauge will allow you to check many dimensions at once, or a complicated dimension that's hard to check, okay? So Lego probably uses a gauge, where you put the Lego on to the gauge, make sure that it fits. So a gauge is usually similar geometry to a mating component, but has much tighter tolerance band, okay? So another set of more interesting tools like this face, it's made with a laser or a white light scanner, so you can get complex surfaces that way. And the thing underneath it is a CMM, so it's a measuring machine that takes a physical probe and touches down all over the part of something and builds a point cloud that you can fit a surface to, and then you can check that surface against your CAD model. So these are just a couple of tools that you would have for checking parts if you get into be a quality engineer. So talking about those engineering roles, this is a lot of work to do to make the design, make the part, and check the part, and that's why in really any industry you'll have different engineering roles, okay? So in industry, you probably won't be called a mechanical engineer or electrical engineer. You'll be a design engineer or a manufacturing engineer or quality engineer. And there's a lot of different titles at different companies or subdivisions of these. You know, if you're a manufacturing or quality engineer, you may be a lean engineer, something like that in your industry. But the principle holds. The design engineer generally is in charge of making the print. So you go, you meet with the customer, you come up with the neat idea, and you make the print. And you feel like you're the most important person, but you didn't make anything. Then comes in the manufacturing engineer. He comes up with the tooling. Like if you want that casting, he makes that casting mold. He creates all those CAM programs. He trains the operators how to make parts. He creates those routers and bill of materials we talked about. And then the quality engineer does all of those inspection things, so creating the criteria, things like that. first article layouts. So when you make a first run of a part in a manufacturing process, you'll lay out the first run, measure every dimension, things like that. Make sure that it's all up to snuff. So that's the general kind of breakout. Like I say, that varies a lot, company to company, industry to industry, but basic concept holds. So traditionally, the design engineer will do all the design, and then when he's done with it, he'll give it to the manufacturing and quality engineers, and they'll make the part. That's a really bad practice, because the design engineers don't know much about making things. So they'll create products that are really difficult to make, really difficult to check. So a more modern concept, and it's not all that modern, but it's very important, is concurrent engineering. So concurrent engineering is bringing those people in, at least at the conceptual design phase, if not earlier, so that as you are designing your part, you get feedback on how it could be made, so that you can work toward making a more affordable part. Okay. So design for assembly and design for manufacture are two pieces of concurrent engineering. Design for manufacture, you're interested in optimizing the system of parts. So if you have 100 parts in an assembly, you're looking at how do I reduce the number of those parts? How do I reduce the complexity of the assembly procedure? And how do I eliminate mistake opportunities? So if you think about this assembly with the handle, that little slot where the cross pin went was on one side. And I created that little chamfer to show you which end it goes in. So you had a lead in, it was easier to put in, and you had a visual cue as to which side to put it in. Because if you inserted it the other way and you went to put your cross pin in, it wouldn't be located properly, right? So you got to think about those kind of things in assembly. Design for manufacture, you're interested in a single part. So how do I make this one part more manufacturable, easier to make? So if you think about like a metal casting, okay? If you're making a part out of a casting, that's a low-cost operation. Machining is very high cost. But if you, as a design engineer, make something that can't be casted and can only be machined, then the manufacturing engineer can't save you that cost later. So you have to design it in up front so that you can take advantage of those methods. So quick example of design for assembly. So this assembly on the left is just a little tray. They've got 24 different parts, 8 different types, several different procedures to make the 4 pieces, main body pieces. And if you brought this design in as a design engineer to a manufacturing engineer and you've already gotten through the design phase and you're ready for production, there's not much they can do about it. Because they could weld it or something instead of putting the screws and bolts in, or the bolts and nuts in. But they can't really save you. But if you bring that manufacturing engineer at the conceptual design phase, they may say, hey, we could stamp this part and make it in one piece with a stamp and bend operation. And we could reduce the cost of this thing by tenfold, right? So this is why you want to do concurrent engineering. Much simpler to assemble this piece with a couple of spring tines on the side and 2 manufacturing processes. Okay? To kind of bring that home, if you look at the difference between incurred cost, which is in blue, and committed cost in red, so this is in a product life cycle. Kind of hard to read, the resolution's bad here, but on incurred cost, as you go through the concept, design, testing, process planning phases, you've only spent about 15% of the actual cost for making the product. And then you spend all of your money in the production phase to actually make the part. Okay? So engineering is cheap relative to actual production. If you look at the committed cost, at the end of the conceptual design phase, you're in at 60% of your committed cost. So what that means is the design that you had can only be made in such a way that you've spent this money. Where if you include your manufacturing engineers up front, that you can get that 60% to be as small as it can be. Okay? So the very concept of your design will dictate most of the cost of it. It's not the production method as much as it is the design. Okay? So if you get into an existing part and you say we need to make this cheaper, and you start thinking about how could we manufacture the same part in a different way, it's a lot more difficult than designing it appropriately to begin with. I think we've got about 2 minutes, which probably is not enough, 1 minute, not enough time for this exercise. If any of you want to practice these skills, which I'm sure you do, a basic concept would be take a 4 or 6 block Lego. You can do a 4 block Lego, simple. Okay? Take a 4 block Lego, draw it out as a print, and try and figure out what the tolerances would need to be for those Legos to snap together every time. Okay? Good? All right. If any of you do that and want me to check it, send it to me. Okay. I see everybody really excited. All right, good? Thank you.